about first-photon imaging.
Thanks for rushing back from a shorter lunch. I'm Vivek Goyal, and so my talk today is on a method for computational imaging that we've named First-Photon imaging. It's joint work with Amit Kirmani, Vivek Goyal, Shin, Andrea Klossler, Franco Long, and Jeff Shapiro. That's two of my students, one co-advised student, two of my former colleagues at MIT, and one of their students. Now, for those of you who don't know me, which is most of you, I'm not a mathematician, but I'm an engineer who likes to talk to mathematicians, and I hope that you appreciate that perspective. And I think you'll see that from the talk, that it's not emphasizing a lot of mathematics, but instead what you can achieve with some interesting accurate physical models and exploitation of the sorts of tools that come from this community. All right, so first-photon imaging is a method to estimate 3D structure and reflectivity of a scene together from only one detected photon at each pixel location. So shown here are some examples of scenes captured with our computational imager at one detected photon per pixel. Now, while the experimental part of this project is significant, I want to emphasize that we do not achieve our results by having unusually short pulse lengths in our laser, or detectors that are unusually fast or unusually low dark currents, or by having a setup that has unusually little ambient light. Instead, we have experimental data that actually presents a very significant signal processing challenge, and then we introduce some new signal processing to address that challenge. So to drive that home, the top row here shows conventional interpretation of our experimental data, and then the bottom row shows what we're able to achieve with that data. So everything I'll be discussing here today is in the realm of active optical imaging, which means that the imaging apparatus includes a light source that illuminates the scene. I'll start with a review of conventional active optical imaging. In conventional reflectance imaging, a scene is illuminated with a light source, and some of that light reflects back toward a sensor. The sensor will generally have an array of photodetectors, and focus of the reflected light onto that array gives spatial resolution from the scene. Quite simply, the number of photons detected at any one sensor pixel is proportional to the reflectivity of the corresponding scene patch, and from this you get an image. So the number of detected photons is proportional to the patch reflectivity. This method of imaging, it gets all of its contrast from the variations in the numbers of detected photons, so it requires a lot of photons to get good contrast. Here I've written thousands of detected photons per pixel for reasonable contrast. You can't disagree with me because I haven't defined reasonable contrast. But a simple sort of back-of-the-envelope calculation reveals that if you think about a photograph that's taken, let's say, outdoor on an overcast day, you're probably detecting at least 10 to the 5 photons per pixel. So typically, images are formed with a lot of pixels. Now, let's switch our attention to capturing depth information, because we're going to capture reflectivity and depth together. A conventional system for forming a depth map of a scene would now use a pulsed light source, and it would have to have a time-resolved sensor. The scene is again illuminated, and some small fraction of the light is going to reach the sensor, and it's important that at that sensor we are time tagging the detection events of the light. At each sensor pixel, one forms a histogram of the arrival times of the detected photons, and that histogram will be a shifted version of the illumination waveform. The shift is by an amount that's twice the distance divided by the speed of light. So by the time of flight principle, one estimates distances at each array location in that sensor array. And doing so forms a depth map. I'm going to show depth maps with false color as shown. All right, so now even in the absence of background light, this kind of traditional method of image formation is going to require, let's say, tens of photons per pixel to get reasonably accurate depth maps. These conventional methods are fundamentally noise limited, so let's talk quickly about how one might model the noise in the scene. And apply denoising methods based on those noise models. To illustrate the effect of noise, I'm going to depict the ground truth as shown here. So A is a point with greater reflectivity than B. So the number of photons detected from A will be greater than the number of photons detected from B. Also, A is a nearer scene point than B. And so the photon detections corresponding to A will come sooner than the photon detections corresponding to B. And here, I just put the A and B waveforms on the same axis just to save space. But we are talking about acquiring data separately at different spatial patch locations. Now, if you're thinking of a realm where you have, say, 10 to the 4 to 10 to the 6 detected photons per pixel, then a reasonably accurate model for the noise in such an apposition is additive white and Gaussian. So you can think of, for both the reflectivity and the time delay, that you have, roughly speaking, the desired quantity plus additive white Gaussian. At lower light levels, like let's say hundreds or thousands of detected photons per pixel, it becomes really inadequate to think about the noise as Gaussian. And you get significant improvements by by using the model that the number of counts is a Poisson distributed random variable with a parameter that depends on the reflectivity. Also, the variance of a time delay estimate becomes inversely proportional to the number of detected photons. So in particular, the variance of the TIJs becomes spatially varying when the NIJs are spatially varying. I'm sorry, actually, what's written here is wrong, but in changing from computer to computer, I've made it uneditable. But this should be squared. So the variance of the TIJs is not the RMS divided by NIJ, but in fact, the square of that quantity divided by NIJ. All right, but we want to talk about much, much lower numbers of photons detected. Not millions or thousands or even hundreds, but going down to, let's say, 1 detected photon per pixel. You can think of that as just a thought experiment, but in fact, we surprised ourselves in terms of what we were able to generate from only 1 detected photon per pixel. We call our method first photon imaging because the way we reduce to just 1 photon per pixel is not to have 1 photon per pixel on average, but actually to have exactly 1 detected photon at each pixel location. In particular, we only use the first one at each pixel location. So, in first photon imaging, we have a pulse light source, we do this illumination, some fraction of the light will reach the detector, and only the first photon is detected at each pixel. As the name suggests, after the first photon detection, we stop. With conventional image formation from this data, what do we have? Well, for reflectivity, it's nonsense. Because we've detected it, we've collected exactly 1 photon at every pixel. So we get this nonsense constant image as the reflectivity if we interpret the data conventionally. The time delays for depth, it does make sense. It looks like a quite noisy version of the depth map of the scene. Okay, and again, I'm sorry, this should not be RMS pulse width, but it should be the mean squared pulse width. It should be squared, divided by 12. It's not, this has the wrong dimension. There should be a square root there. Okay, but this is nonsense on the left for reflectivity, and this is very noisy on the right for depth. So we're going to have to do something different with our data than just the conventional interpretation. Now, in addition, in most practical settings, there's a non-negligible amount of background light, and this background light severely degrades the imaging quality. Okay, and in particular, well, that doesn't change our nonsense image on the left, but when you have a significant amount of background noise, the variance of your time delay estimate becomes proportional to, again, sorry, we should say proportional to the square of the pulse repetition period, or proportional to the a priori ambiguity period. So again, we'll want to do some new interpretation of this data to form much better images for these data. So what's that going to be? Well, we're going to first look at the physics of the detection a little bit more closely, and then make a couple of very simple observations that enable us to form interesting images. All right, so let's get a little bit more specific about the detection. And here I'm actually tuning it a little bit more towards exactly what we implemented as an experiment. So when I talked about conventional acquisition, I was implicitly assuming having a detector array in both the case of reflectance imaging and depth imaging. Now, let's suppose that we're getting our spatial resolution by raster scanning with the light source, because that's what we actually implemented with our system. It's really analogous, and you could say it's just a matter of multiple reciprocity or whatever. But we use a raster scan pulse light source. So the spatial resolution comes from varying across the scene, like I'm doing with my laser pointer now. Now a little bit of light will come back towards our detector, which is a single photon avalanche detector, SPAD. We use time-correlated detection, which just means that the light source and the detector can be put on a common time axis. And we record something from each one of these pulses. Now, what should we actually be seeing at the detector? Actually, it was great that the last talk before lunch talked about Poisson processes. I was going to just use Poisson processes as if, everybody's familiar with Poisson processes. And I'm glad that the last talk was kind of the joy of Poisson processes or something like that. So, what we're going to get in the absence of any background is at the detector arrivals in an inhomogeneous Poisson process. By inhomogeneous, I mean that the rate function of the Poisson process is not constant. There's no adjective there. By default, a Poisson process is homogeneous, meaning that it's constant in time. An inhomogeneous Poisson process has a rate function that's here denoted lambda ij of t for the pixel patch ij. The rate function of this Poisson process is a scaled and shifted version of the illumination waveform. The shift depends on the distance to the scene point, Cij, and the scaling depends on the reflectivity, alpha ij. When we have background light or dark counts, then the background, that noise, those two sources of noise, will also create detection events. Those detection events are arrivals in a homogeneous Poisson process. So that is a Poisson process that has a constant rate function that's here written p lambda. Taking the two together, we actually have a merged Poisson process, and it has a rate function that depends on all of these parameters. Now, in the way we've defined first photon imaging, not every incident light pulse has to create a photon detection. So when there's no detected photon from the first incident light pulse, we pulse again. Maybe again there's no detection event, and maybe on the third pulse we get a detection event. Now, we're not going to be able to tell whether that should be, let's say, labeled orange or labeled in blue. We don't know whether that detection event is due to light that reflected off of our scene or due to background light. We'll get back to that later. But we will get a detection event that has come from this merged Poisson process. So we define two random variables from this experiment at each patch location ij. Nij is the number of pulses transmitted before the first photon detection, and Tij is the detection time relative to the time of the last pulse emission. Tij is a completely conventional quantity, completely conventional. Nij seems to be something that people didn't really think to collect before. So very often, instead of noting the number of pulses transmitted before a detection, that would just be ignored. So now, how do we interpret these? Well, Nij encodes the reflectivity alpha ij through a geometric distribution. What do I mean that it encodes it? Well, Nij is a geometric random variable with a parameter alpha ij, and there's an invertible function that relates the parameter of the geometric random variable to alpha ij. Tij encodes the depth zij. What I mean by that is the PDF of Tij is a normalized and shifted version of the illumination pulse shape. Again, this interpretation of Tij is completely conventional, but it does not seem that Nij has been exploited before in any works. All right, now looking at this in a little bit more detail, it's easy to derive the probability of having no photon detection in one period, and that directly gives us the parameter of the geometric random variable. The PDF for Tij is actually a mixture distribution. It has two different simple forms. There's a simple form in the case that the detection is due to ambient light. In that case, Tij is uniformly distributed. It also has a simple form in the case that Tij is due to the signal, because then we just have a normalized and shifted version of the illumination waveform. So Tij has a mixture distribution mixing these two together. And in our experiments, we actually have a very significant probability of a detection event being due to noise. We actually have about half of the detection events being due to noise. So you could also think of that as 0 dB SNR, in addition to having only one detected photon. All right, so we do this raster scan illumination to collect first photon data, and let's see how we're going to use that. Well, first of all, this is what the data looks like. So on the left is what raw Nij data looks like, and it has a natural, it looks as it ought to. Darker parts of the scene, like off the t-shirt, it takes more pulse repetitions until you get a detection event typically, and so the dark parts of this shirt lead to larger values of Nij. And the Tijs, well, it looks like a depth map, but a very noisy one. Conventionally, one would just do point-wise estimation, and this is the result of point-wise estimation, where we've overlaid an estimated reflectivity on top of an estimated position in 3D space, and we rotate the model around so that you can see that we're talking about something that's 3D. All right, so how do we form images instead? Well, we want to combine that physical model for the acquisition with the exploitation of spatial correlations. And again, exploitation of spatial correlations is old hat to this community. By exploiting spatial correlations, what I mean is you can think of the reflectivity and the depth both as approximately piecewise constant functions. A pixel, in both the reflectivity and depth of a pixel, is usually rather close to the values of its neighbor, except around an edge, and you want to maintain the sharpness of those edges. All right, so we estimate the reflectivity. We're going to go through 3 steps. So the first one is to estimate the reflectivity from the pulse data. I think I didn't pause and point it out so clearly, but in that probabilistic model that I showed you, the Nijs and the Tijs are decoupled in the sense that the reflectivity depends only on the Nijs and not on the Tijs. So we can estimate reflectivity from the Nijs alone. We do that with a regularized maximum likelihood estimate. The regularization is by the L1 norm of wavelet coefficients. Again, a standard sort of approach for this community now. But I do want to point out that there's something very lucky here as well. The lucky part is that the natural data fidelity term, which is the negative log likelihood function that comes specifically from that geometric distribution, that term gives us a convex problem here. So we use the L1 norm of the wavelet coefficients, but also are lucky in terms of the form of the natural data fidelity term. So I'll show you now. This is the result of denoising the reflectivity. The denoised reflectivity is still being rendered on a noisy point cloud. So it looks strikingly denoised only from certain angles because the 3D structure is still very noisy. Now, you might think that since I'm saying regularized maximum likelihood estimation makes so much sense for the reflectance, I should just do the same thing for the depth and I'd be done. And in principle, that's true. That would be a reasonable approach, except that one doesn't get so lucky for the depth. So because of that mixture distribution, you can't just put in the natural data fidelity term and get a convex problem. The contribution of the background light into the log likelihood term gives you something very, very far from convex, kind of hopelessly far from convex. And so we insert a second step of trying to remove most of the detections that are due to noise. Then we'll go back to a regularized maximum likelihood estimation of the depth. That noise removal step is really about trying to distinguish between two distributions. There's the uniform distribution that arises when a detection is due to background light, and then there's the more peaked distribution that's due to light that's actually reflected back from the scene. We design a statistical test based on the rank-ordered absolute difference statistic. So what that is the sum of the four smallest absolute differences between a pixel value and its neighbors. So what happens if that number is small? Well, if that number is small, then probably the particular pixel that I'm looking at has a Tij that is due to light that's actually reflected from the scene. If that number, the road test statistic, is very large, on the other hand, probably the detection event at this patch Ij is due to noise. So we use this test statistic to censor the noise. And a principled good choice for this threshold in this test depends on the reflectivity estimate that came from step 1. So we're really getting a benefit from step 1 in step 2 here. So here's the result of that noise censoring. And you can see that this is considerably cleaned up from what we had before. However, it's worse around the edges, and it's also worse in the darkest parts of the scene. Both of those are kind of what we'd expect. But now that we've gotten rid of most of the detection events that are actually due to background, we can make believe that there is no background. When we make believe that there is no background, then we get a data fidelity term that is convex. And so we can do a regularized maximum likelihood estimate by solving a convex problem. And that leads to this final result. And so our 3-step reconstruction process gives us this reconstruction from only one detected photon per pixel, even though about half of those are due to noise. So it's kind of half a signal photon per pixel and half a noise photon per pixel. This just compares what we started with what we've achieved. All right, we've done more evaluation, but I don't have time to talk about that in detail. Remember, we're talking about real data collected with a real system. The raster scanning is with the Galvo, detection is with the SPAD, time tagging is with a device called HydroHarp from PicoQuant. We did some evaluation based on test charts. Here's a depth resolution test chart made by having squares of different thickness pasted to a board. And here's a more standard sort of resolution test chart. So we did tests with these kind of test charts to try to quantitatively evaluate the performance of our computational imager compared to conventional processing of this same kind of data. We've also done comparisons against different kinds of post-facto processing of the data, like the BM3D algorithm, which is maybe a leading denoising algorithm for 3D data. And our processing does significantly better because it more accurately, it's based on more accurate modeling of the physics of the acquisition process. We've also imaged various other natural scenes, and we've tested the repeatability of our experiment, which again I'll not dwell on. So there are certainly limitations to our approach. There's higher error at corners and lateral surfaces. Of course, lateral surfaces are where you get very little reflected light, so that's just a fundamental problem. This sort of method does fail at high optical flux because we're exploiting dynamic range in that Nij variable. If the optical flux were high, then the NIJs would be small. There'd be very little dynamic range in the NIJs, and we could even, one could push that to an extreme where the optical flux is so high that all the NIJs are 1, and then this style would not work. But that would be a very inefficient way to do imaging anyway. That's not a typical way to do LiDAR-style imaging. We also have not yet modeled the multi-path contributions to these signals. There are various kinds of extensions that we already have started, and some of them are essentially finished, like incorporating multiple photon detections per pixel, having fixed dwell time per pixel instead of this notion of moving on as soon as you detect a photon. We've investigated sensitivity to system parameters, and we've derived various estimation theoretic and bounds on performance. So naturally, our approach can be used for 3D imaging. What we've shown so far is a laboratory scale experiment. We're now moving toward honest-to-goodness remote sensing at long range. Things of a room scale are also interesting, at least for consumer applications, say, but there it's important to lower the hardware cost, and we're exploring that as well. And finally, the techniques that I've described here today have applications in biological and chemical imaging where lower light levels are sometimes crucial because the samples that you're trying to image can be damaged by light. The main published reference on this work was in the first issue of Science this year, and everything takes longer than you expect, so this is really bad form, but I'm promising that we'll put something on archive by the end of March. I think that's very conservative because there's already a complete draft of a paper that has new processing beyond what I've described here, as well as more analysis. So if you're really interested, please expect to find a paper on this within about a month. All of the data I've shown you and all the code that's used to generate everything I've shown you is actually available online. So there's a web page for this project. And I invite any questions. Thank you very much.
We have time for 1 or 2 questions.
So essentially, the time arrival, because you have the Poisson process, is governed by the exponential distribution. So you want to estimate the mean of the exponential, correct?
Well, the mean or the min?
The mean, the average.
We could do that. I mean, okay, please go finish your question. Sorry.
Because you assume that the mannequin at least is still, the distance doesn't change between the mannequin and the camera. So, and since the light is pulsating more, wouldn't you have a more accurate estimation of the depth if you take the means of the arrival time?
Okay. So I'm certainly not trying to say that using only the first detection is better than using the first 100 detections. So, I mean, if you detect more photons, you should be able to do better. But I'm just showing you a way to get good images from only one detected photon. And actually, okay, so this paper, which will exist very soon, at least in a version on archive, will show performance as number of detected photons varies. I'm not trying to say that it's better to detect fewer photons than more.
No. What I'm saying is each time it pulsates because the light dies completely. The beam dies completely. Its pulsation. During its pulsation,
yeah,
you have interruption of the light, of the laser.
Oh, sure. The pulse width.
Okay, so you have 100 times, 200 times in one photon experiment.
Okay. I guess
But if you average the arrival times there, you can have probably a more accurate estimation of the depth.
So, if I use more detection events, sure, I can get more accurate depth estimates. I think what you're getting at is maybe time efficiency versus photon efficiency. Maybe that's what's underneath your question. I've been focused on photon efficiency rather than time efficiency. So in terms of performance as a function of number of detected photons, I'm not claiming this is the best possible, but I am claiming it's pretty darn good. Okay? Quality as a function of number of detected photons. It's a different question to say quality as a function of the amount of time it took you to acquire data, And there, I mean, there are all kinds of different things you could do, and we should talk about what's held constant. Is your illumination peak power held constant? Is something else held constant? There are a lot of different variables that can be changed here.
What was the question?
So I have a question that you use this two-map estimation, right? And you use this wavelet, this sparsity prime. Is there any scope of augmenting this cost function to introduce other edge priors like Hilbert priors or something like that?
Sure thing. So in fact, we were intentionally keeping the estimation process very simple here. The regularizer is very simple. Like you're pointing out, we could regularize with something more interesting than just the L1 norm of Dolce wavelet coefficients. We use that simple regularizer because readers of science could understand that regularizer. The people in this room would understand much more complicated regularizers, and it would make sense to include different kinds of regularization. I mean, another thing that I didn't point out, but it certainly makes sense to include regularization that couples the alphas and the z's, but we didn't do that either. And I think there's a lot of, that's a fun mathematical
Because you
problem.
mentioned this problem with edges, that you had this problem. So
Yeah.
and you just mentioned, so how about, because you have this two maps, two data that you have, so how about a mutual information that you can borrow information about this patient?
Yeah, that's what I was getting at when I say when you the alphas and the z's. Even if let's say I was just still fixated on wavelets, I should in the wavelet domain I expect significant coefficients to appear in the same locations roughly, because significant coefficients are mostly coming from edges, and edges in depth and edges in intensity are certainly very, very highly correlated. A depth edge almost always leads to an intensity edge. Sometimes you have intensity edges without depth edges. Like, you know, if you're wearing striped clothing, then you have intensity edges without depth edges. But they're highly correlated. So one could incorporate a lot more interesting regularizers. I guess I phrased it as regularized maximum likelihood. You called it MAP, but that's fine with me too. We could phrase this as a Bayesian approach as opposed to a regularized
Yeah, but that comes from medical
Yeah.
imaging, so it's the same name. Penalized
Absolutely.
likelihood, you can say.
Absolutely.
Well, let us thank our speaker again.